Welcome to The Explainer. So, what is reality? I mean, what is it really? You'd think physicists would have that figured out, but it turns out the deeper they look, the weirder things get. Today, we're taking a journey right into the heart of that mystery, quantum mechanics. And hey, before we dive in, let's start with a bit of a warning. This one's from a true legend, Nobel laureate Richard Feynman. He said, "I think I can safely say that nobody understands quantum mechanics." And honestly, that quote is the perfect starting point for the absolute weirdness we are about to get into.
All right, so here's the plan for our tour through some of the strangest ideas in all of science. We'll kick things off with a quantum mystery, then look at ideas like riding an invisible wave, splitting into infinite worlds, getting information from the future, a pre-written universe, and finally, the bizarre role of the observer. Yeah, buckle up, this is going to be a wild ride.
Okay, so first up, a quantum mystery begins. And to understand pretty much everything that's so weird about the quantum world, we only need to look at one experiment. It seems simple on the surface, but this is the one that basically broke physics. So let's start with something that actually makes sense. Imagine you're firing tiny particles, like little electrons, through a single slit in a barrier. What do you get on the screen behind it? Well, you get a single band, right where you'd expect. So far, so good. This is exactly what our everyday intuition tells us should happen. But what happens when we just add a second slit? It seems like such a tiny change to the experiment, right? Well, this is where our entire understanding of reality just completely falls apart. Instead of getting two simple bands like you'd expect, you get this bizarre interference pattern of many bands. That's what waves do when they interfere with each other. But here's the kicker. This happens even when you fire the electrons one at a time. It's like the single electron somehow goes through both slits at once, interferes with itself, and then decides where to land. How in the world does it even know that second slit is open? This happens with atoms, even big molecules. It's nuts. So physicists came up with this idea called the wave function. You can think of it as a cloud of all the possible places the particle could be. But the second we try to measure it, or even just look at it, poof, that cloud of possibilities instantly collapses, and the particle appears in just one single definite spot. So what's causing this collapse? What turns that wave of possibilities into a single, concrete reality? That right there is the central puzzle we're trying to solve. All right, let's get into our first possible solution. Our first stop on this tour is an idea that tries to keep things simple, the pilot wave theory. It wants our particles to just be, well, particles. So the pilot wave theory says, look, the electron is just a particle. It's always in one place, but it's being guided, kind of like a surfer on an invisible pilot wave. This wave fills all of space. It's the thing that goes through both slits, creates that interference pattern, and then basically tells the particle where it needs to land. It's a neat solution, right? The particle goes through one slit, but the wave guiding it goes through both. But there's always a catch, isn't there? And this one is a doozy. For this to work, that pilot wave has to be non-local. What that means is that the wave instantly knows about everything in the entire universe, all at once. So if you poke the wave over here, a particle on the other side of the galaxy could be affected instantly, faster than the speed of light. This is exactly what Einstein hated, calling it spooky action at a distance. You see, Einstein really hoped that reality was local. He believed that things have their properties whether we look or not, and that absolutely nothing can travel faster than light. But, and this is a huge but, a series of mind-blowing experiments proved him wrong. In fact, the 2022 Nobel Prize in Physics was awarded for proving that this spooky action is a real, undeniable feature of our universe. It's not a theory, it's a fact. Reality is non-local. So if spooky action at a distance is just a little too much for you to swallow, don't worry. Our next interpretation gets rid of it completely. The only catch? It replaces it with something, well, something even more bizarre. Welcome to the many worlds interpretation. Okay, get ready for this. The many worlds idea says, but the wave function never actually collapses. Instead, every time there's a quantum choice, like an electron going through the left slit or the right slit, the entire universe splits into two. So in one universe it goes left, and in a brand new parallel universe it goes right. Every single quantum measurement creates a whole new branch of reality. Yes, that means there are infinite versions of you out there. Now, you might be thinking, why on earth would anyone believe that? Well, it's because of a fascinating trade-off. If you get rid of that messy, unexplained wave function collapse, the math becomes incredibly elegant and simple. It's beautiful.
The only price you have to pay for that mathematical purity is, well, you have to accept that there's an ever-growing, infinite number of parallel worlds with infinite versions of you. All right, our tour is about to take a really sharp turn, one that messes with something we all take for granted, time itself. What if cause and effect isn't a one-way street? What if you could get information from the future? This idea is called retrocausality. It suggests that effects can happen before their causes. So when you decide to measure the electron on that screen, your choice literally sends information backward in time, influencing the particle right at the moment it was fired. The particle seems to know what to do because, in a sense, your future decision already told it which path to take. Mind-bending, right? Okay, so what if you don't like spooky action or infinite worlds or time travel? Is there an interpretation that gets rid of all that weirdness? Yes, there is. But the price it asks you to pay might just be the highest of them all. This is superdeterminism. Superdeterminism argues there is no randomness, none. The particle's path wasn't a random choice. And here's the kicker. Your decision about how to measure it wasn't a free choice either. Everything, every particle, every thought, every action was perfectly determined, all choreographed at the moment of the Big Bang. And if that's true, it means free will is completely and utterly an illusion.
Here's a good way to think about it. Imagine a scientist is testing if smoking causes cancer in mice. They'd split the mice into two groups randomly, right? Well, a superdeterminist would come along and say, nope, it wasn't random. They'd argue the universe was secretly set up from the very beginning so that the mice that were already going to get cancer would always end up in the smoking group. It's a kind of cosmic conspiracy where the scientists' free choices are secretly linked to the mice's health to create a misleading result. And that's what superdeterminism says about quantum physics.
Okay, time for our last stop on this bizarre tour. We're going to the oldest, most famous one of them all, the Copenhagen interpretation. This is the one you usually learn in textbooks. And you know what? It might just be the weirdest one of the bunch. So what does Copenhagen say? It basically says, the wave function collapses when you measure it, period. It doesn't try to explain how or why, it just does. And this is what leads to the famous paradox of Schrödinger's cat. You put a cat in a box with a quantum trigger. Until you open that box and look, the cat isn't alive or dead. It's in a quantum superposition of being both alive and dead at the same time. Reality is a blur until someone observes it. But that raises a huge question. What counts as an observer? A camera? A cat? Or does it have to be a conscious human being? This gets even weirder with a thought experiment called Wigner's friend. Imagine your friend is in a sealed lab with Schrödinger's cat. Your friend opens the box, and for them, the cat is either alive or dead. The wave has collapsed. But for you, outside the sealed lab, you don't know the result. So from your perspective, your friend, the cat, and the entire lab are now in one giant superposition. This paradox led some physicists, like Eugene Wigner, to a shocking conclusion. Maybe consciousness, a thinking mind, is the one thing in the universe that can collapse the wave function and turn possibilities into reality. And that brings us all the way back to Einstein's famous haunting question. He asked a colleague, do you really believe the moon is not there when you are not looking at it? If reality truly needs a conscious observer to become, well, real, what happens to the universe when no one is looking? Does it all just dissolve back into a blurry fog of possibilities? Every single one of these interpretations, no matter how bizarre it sounds, is a serious scientific attempt to answer that very question. This whole explainer has been based on the quantum mechanics section of the book Simulated Reality. If you want to dive even deeper down this rabbit hole, you can find a link to the book right there in the description.